lesson, I'm going to introduce the concept of spontaneous processes and entropy. But we're going to build on that quite a bit throughout this big idea and the rest of the year. So a spontaneous process is one that proceeds on its own without any outside assistance. So entropy, as I'd said in the previous lesson, is a measure of the randomness of a system. And so the second law of thermodynamics ties spontaneous processes and entropy together by stating that the entropy of the universe increases in any spontaneous process. So if you look at the transition from ice to liquid water to water vapor, the entropy increases. And the entropy increases because in ice, the only motion that really occurs is the vibration of those molecules because they're holding on to one another so tightly. In contrast, once you have liquid water, those molecules are going to not only vibrate, they're also going to rotate around one another. And then there's a little bit more freedom for what's called translation, meaning just the linear movement of those water molecules. In water vapor, not only can they vibrate, rotate, but they can but they are free for translation as well, meaning just that linear movement. So water vapor has a lot more freedom and therefore has a lot more disorder and therefore a lot more entropy. So the third law of thermodynamics states that the entropy of a pure crystalline substance at absolute zero is zero, meaning it has no disorder. Well, using that concept, the entropies of specific molecules and atoms were determined at the standard state, meaning 25 degrees Celsius and 1 atmosphere. And so what we can do is actually use those, it's in Appendix C, and calculate the entropy changes that occur in chemical reactions. One thing that you'll notice when you look at Appendix C, the entropy of a solid, a liquid, and then a gas. Gases obviously have the highest entropy, as I'd stated in the previous slide. Notice really quickly how there's a sudden jump in the entropy as you go from a liquid to a gas and a solid to a liquid. And so this demonstrates that while water is present on that appendix, it exists as water solid, water liquid, water gas. So be careful because those values for the standard entropies are very different. So to calculate the change in standard entropy, this should look really familiar. It's the sum of the standard entropies of the products minus the sum of the standard entropies of the reactants. And we actually did that with enthalpy previously. So what we're going to do is, in order to calculate the standard change in entropy, that's going to be equal to 2 times the standard entropy of aluminum plus 3 times the standard entropy of water. Notice this is going to be water gas, so be careful with that, minus the standard entropy of aluminum oxide plus 3 times the standard entropy of hydrogen gas. Okay, and so when you look those up in Appendix C, it's going to be 2 times 28.32 plus 3 times 188.83 minus 51.00 plus 3 times 130.58. And so what you should end up getting for the standard entropy change is 180.39. Notice the units. It's joules per Kelvin. The units for standard entropy change are joules per mole Kelvin, but because you multiplied by the coefficients, which represent the number of moles, the final units are just going to be joules per Kelvin.